I was like, fine.
Alrighty, good morning everybody, and welcome back to Calc 1. Plan for today is I have a quiz for you on Standard 7, and then we are going to continue our discussion from last class about Standard 8. Office hours, got my usual office hours, today at 11 and at 2, tomorrow at 10 and at 1. Don't forget, this Friday will be our first exam. Standards 1 through 7, and also you have a couple of old web work stuff with due dates tonight and Friday. Any questions or comments before we get started for today? Yes?
What did you say we could bring with us to the test again? Was it a piece of paper or a note card?
A sharp wit and a good attitude.
Okay.
And with that, also one sheet of note, front and back, whatever you would like written on it.
What are we doing tonight?
Like, am I crazy?
Yes, no, you're not imagining things. You can bring a sheet of notes with you to the exam. There are questions or comments? Okay, what do mathematicians call a couple of MDs?
Pair.
A what?
Pair.
Specifically, a paradox.
Well, close.
Okay. And with that, go ahead and do the quiz. I'll pass stuff back after the quiz for today. We've got a lot of stuff to pass back. And put everything away. It is quiz time.
I didn't think I'm very good dressed this morning. Bacon bits, eggs.
I have the egg hash brown. You can mix it up, and it's just all the same consistency.
Okay, quiz is out. So quiet in the room, please. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Quizzes in, please. Alrighty, I have a big pile of things to pass back. So without further ado, Hannah. Oh. Kyra.
I didn't bring any.
Aiden. Riley.
Yeah, that's before. Yeah, I wrote it in the next script.
Joseph.
We all went that way.
I do.
Will.
Alright. I think I did.
Emily.
Then you probably should. I probably should because I can't remember if it. I remember when I was so sick, I thought I overdosed on like these snacks.
Let's see, Rachel. Brendan.
I feel like you did full time from that.
I was fine.
Kinsey.
When I get really sick, I'll take an NyQuil and
Avery.
Cute.
you're like, please.
You're like, I'm using my ass out.
Petro.
It's the only time I dream.
Oh.
I don't have dreams.
I feel like I do.
That's not true. This summer I had a nightmare that I had fleas.
That's fair.
Colin.
I was supposed to from the training until, I was like, I was in the training. And the trainer, like, doing stuff like this. And then
Oh, Vera.
I just like made my arm, just like put it behind my back.
Okay, but I forgot
Like,
this.
pop out.
Zach.
She's like, "Dude, that's not too bad." Is this Morgan? Yeah.
God, I don't know.
I told her, I said, I can't really reach behind my back now.
And again.
I'm trying to just see how far you can. Definitely missed that. I went back.
I also do that. I think it's just
It's
like
like
my
Logan.
Oh, I don't hang around where I did this.
I know, but I did. Like,
Oh,
I just-
I don't know where I came from.
Did you get 1 over X?
X squared plus 1,
Stupid math.
and then -1.
I
Let's move it up top.
And
Yeah, my JQ.
What did you get?
I did some. I was
okay, a couple general comments. This is everything that I had, so like all retests and stuff. So based on what you have, you should know your mastery is going into the exam Friday. I have not actually updated Canvas yet with everyone's mastery totals because I figure I would wait to grade today's quizzes. I'm gonna try and grade today's quizzes this afternoon. And when I do, I'll go ahead and put everyone's mastery totals up on Canvas so you can look and easily see which standards you need masteries in going into Friday's exam. As a reminder, if you have 2 masteries in something, you do not need to do that question on the exam. And in fact, I encourage you to skip it. And this won't become super relevant until later exams, but if you don't feel like you're ready for a question on the exam, don't feel like you have to put something down for it. As a reminder, a J and an N on an exam question affects your grade the same way, which is not at all. So if you want to go into the exam with the goal of only earning, say, 3 or 4 masteries, go for and spend a lot of time on those, go for it. This will be more relevant once we get to the second exam, and there's like 15 different pages on the exam, and you're being tested over almost every mastery. But for the time being, I think this exam is doable in a single class, the whole exam. But second exam and onwards, you'll definitely have to start prioritizing.
So we have the whole class period to do the exam?
You will have the whole class period to do the exam. And if you finish early, you can leave early. Any other questions or comments about the exam? Alrighty, so let's get back to standard 8 then. So when we left off last class, we were looking at implicit differentiation, which was the process of how do you differentiate something that's not actually a function, something that's defined. I think last time we looked at the example by an equation involving both x's and y's showing. So last time we looked at the unit circle, x squared plus y squared equals 1, and kind of found how implicit differentiation can be used to find the slope of that circle at a couple different points. And what we found is when we differentiated, anytime we differentiated a y expression, you get a y prime term pop up, owing to the fact that when you differentiate y squared with respect to x, you always need a y prime or a dy dx according to the chain rule. And we ended up finding some expression that was in terms of both x and y. And so what I'd like to do today is to look at a few more examples of putting implicit differentiation into practice, just to make sure everybody is on the same page. So let's see, which one do I want to do? Let's do this one. So I'm going to be on the second page, and I want to look at the curve y to the 4th minus 2y is equal to 4x cubed plus x. Which if we graph out is going to look something like this. So we got this sort of weird looking curve here. It's almost like a sideways parabola, but with like a, a little bit of a bump, a little bit of a bulge in the middle of it. And what I would like to do is to find a formula for y prime. Or if we prefer, using Leibniz's notation, a formula for dy dx. So what we're going to do is we're going to take this equation and we're going to differentiate with respect to the variable x. Dr. Gerstle, what does wort mean? Other than sounding kind of cool, a nice little bit of onomatopoeia, lighten up your day. WRT is my shorthand for with respect to. And anytime that we're looking at a function or an expression like this with multiple variables, I think it's good to keep in mind to not just say differentiate, but differentiate with respect to x, like find dy dx, or y prime of x. So let's see what happens when we do this. On the right-hand side, we will get 12x squared plus 1 when we take our derivative. What are we going to get on the left-hand side? How about when we differentiate y to the 4th with respect to the variable x? Yeah.
You get 4y cubed times dy dx.
4y cubed times a dy dx. Why did you have this? Where did this dy dx come from?
Because we're differentiating with respect to x, and y is not x. We have to sort of treat it as its own function, so we kind of use the chain rule.
Yeah, that's exactly it. the fact that when we differentiate y to the fourth, we would first of all use the power rule and differentiate normally to get a 4y cubed. But then we have to multiply by the derivative of the inside expression y, which when we differentiate with respect to y with respect to x, we get this times dy dx term. Or if you prefer, you could write this out as 4y cubed times a y prime. How about the minus 2y? Henry and Danielle are grinning over there. Rachel?
Would it be minus 2y prime?
Minus 2y prime? Yeah. The minus 2y differentiate to give us minus 2. And then multiplying by the derivative of that y term is going to give us a minus 2y prime. Since we started using dy dx, I'm going to write minus 2 dy dx instead. Nothing wrong with saying minus 2y prime here, but I want to try and be consistent for at least this problem. We started this, Sam chose to start this problem with dy dx, so I'm going to continue with that. But if you wanted to write this as 4y cubed times y prime minus 2y prime, that's also totally okay. It's just another way of writing the same thing. So now we have 4y cubed times dy dx minus a 2 times dy dx is equal to 12x squared plus 1. If we want to solve for dy dx, how can we get dy dx by itself here? Josh?
You just factor it out.
Okay, so if we factor out a dy dx, what are we going to be left with on the left-hand side?
Dy over dx times 4y cubed minus 2.
Like that?
Yeah.
Okay. We have factored out a dy dx from the left-hand side. And now that we have this factored out, what can we do to get dy dx by itself?
Divide both sides by 4y cubed minus 2.
Yeah, we can divide both sides by the 4y cubed minus 2 to get 12x squared plus 1 divided by 4y cubed minus 2. And then I think that is going to be our answer. Just like with our circle, when we did our implicit differentiation and solved for y prime or dy dx, we end up with an expression with both x's and y's in it. And so if you wanted to then find the slope at a particular point, like let's say at, I don't know, hard to find points on this curve off the top of my head. Let's say at the origin, we could then just plug in 0 for x and for y into this equation and find that the slope at the origin is going to come out to a negative 1/2. Because if we plugged in 0 for x and y, we'd get a plus 1 over minus 2 to get negative 1/2. So in general, if you have multiple terms with dy dx showing up inside of it on the same side, like this, to get a single dy dx, just factor it out. Yeah, John?
Are you ever gonna ask us to graph it on a quiz?
What do you think?
No. Or yes?
Not yet, but eventually.
It's not something like this. I might expect you to remember that something like x squared plus y squared equals 1 looks like a circle, but something like this, honestly, if you'd asked me to graph that and I hadn't already cheated ahead of time and put it into and looked it up online, I wouldn't have been able to graph this one for you. Eventually, we're going to talk about how to graph functions using lots of information about the derivative and such. But this isn't even a function. It's just kind of this funky looking curve. So no, you don't have, no, I'm not going to ask on a standard A quiz for you to graph something like this.
Okay.
I would either give you a graph to look at or just not bring up the graph at all. Any other questions or comments? Look at this next one. Square root of x plus y is equal to 1 over x plus 1 over y. This one sort of looks like a y equals 1 over x almost, except it's only in the first quadrant, where x and y both have to be positive numbers to satisfy this equation. And this one is going to get a little bit dicier. So first of all, let's maybe start off on the right-hand side this time, because the right-hand side to me looks a little bit easier. How would we differentiate this 1 over x term?
Negative x to the negative 2.
Yeah, because we could just write this as x to the negative 1. And if we use the power rule of x to the negative 1, that'll give us a negative x to the negative 2, which is the same as a negative 1 over x squared. In a similar note, how can we differentiate 1 over y? Or y to the negative 1 power? Well,
It would just be negative y to the negative 2 dy dx.
yeah, we're going to have a negative, just like we did with the x. When it was x to negative 1, we'll get a negative y to the negative 2, or negative 1 over y squared. And since we just differentiated with respect to y, I agree we're going to have a dy dx term popping up. But since I feel like being a little bit contrarian here, I'm going to put a y prime instead. Just so that you're used to kind of seeing both notations. I think Rachel was itching to have a y prime in the previous problem. Again, it doesn't matter which you use here, as long as you're consistent about it within the same problem. If we had a y prime on the right and a dy dx on the left, that would just kind of be awkward to work with. We have different notations going on for the same thing. So, time to tackle the left-hand side. Square root of x plus y. A little bit scary. Josh, what are your thoughts?
Can you chain roll it?
I think we would have to, because we have a sum, and we also have a square root going on outside of the sum. So I think to differentiate this expression, we'll need to use the chain rule in order to do it. Okay, Josh, so what are your thoughts on how we could use the chain rule here?
Well, your g would equal the square root of x, and your h would be x plus y. And then
Okay,
your g prime of h of x would be 1 over the square root of x plus y. And your h prime would be 1 plus dy over dx or y prime.
you just threw a lot at me there.
Sorry.
I think I mostly kept up. So you said that the outside expression, sort of the g here, is going to be just taking the square root. And that your inside expression, the h, is going to be x plus y. So when you differentiated each of these, you got that g prime is 1 over 2 root x. H prime came out to just 1 plus a y prime. Technically 1 plus 1 times y prime, which is just the same as y prime. And so then when we toss all that into the chain rule, Josh, what is that going to come out to?
It would be 1 plus dy dx over the square root of x plus y, or y prime.
Okay, so we're going to get, you did a couple things there. I'm going to split what you just set up into 2 steps. So we're going to get, don't be sorry. We're going to get 1 over 2 square root of x plus y. So this would be our g prime of h term. And then you multiply that by the derivative of the inside, the inside being x plus y, to get a 1 plus y prime term. And then when you separated that out, you got 1 plus y prime over 2 square root of x plus y. And go ahead and put that y prime in the numerator too. Does that sound good? Yeah, so what Josh did was he used the chain rule to help differentiate square root of x plus y here, keeping in mind that in order to do that, even though we have y showing up, it's still kind of, the chain rule behaves the same way, in that we have derivative of outside plugging in for x here, the inside expression, x plus y, and that gave us our 1 over 2 square root of x plus y term. And then multiply that by the derivative of the inside expression, x plus y, which gave us this 1 plus y prime. To get 1 plus y prime over 2 square root of x plus y is equal to negative 1 over x squared minus a y prime over y squared. Good golly gosh, how on earth are we ever going to get y prime by itself here? What's that say? Well, it's kind of scary. Because right now we have y prime showing up on both sides of our equation. We have one here on the left-hand side and another one on the right-hand side. So it's not just as simple as factoring out a y prime or a dy dx from a single side, like we did in the previous problem. Wynn, what are your thoughts?
I would start out by separating the fraction on the left.
Okay, so how can we do that?
1 over 2 square root x plus y plus y prime over 2 square root x plus y.
Okay, I think that's a reasonable thing to do. We can always take a fraction like this where if we have a sum in the numerator, we could split it apart into 1 over denominator plus y prime over denominator. So that'll give us this lovely looking expression. Sam, what can we do from here?
Can you subtract 1 over 2 radical x plus y from both sides?
Okay, so that'll give us a y prime over 2 square root of x plus y is going to be equal to negative 1 over x squared minus y prime over y squared minus 1 over 2 square root of x plus y.
And then add y prime over y squared.
Then add this term to both sides?
Yeah.
Why would that be helpful?
Because then you get both of the y primes on one side.
Ooh, okay. That sounds like we might end up with a situation like we did in the last problem. Okay, I'm on board. Give me an eraser. So then if we do that, we're going to get what? Y prime over 2 square root of x plus y prime over y squared is going to be equal to negative 1 over x squared minus 1 over 2 square root of x plus y. Let's get someone from the right half of the classroom here. So now, Sam and Wynn have done the task of getting the y prime term, the two terms with y prime in them, on the same side of the equation. And then the stuff on the right-hand side has x's and y's, but no y prime terms. So what can we do from here? Elise?
Wouldn't we just need to multiply both sides by 2 square root of x plus y over 1?
Multiply both sides by 2 square root of x plus y? We could do that. We can do that. All right, let's do that. So if we multiply both sides of this equation by 2 square root of x plus y, then on the left side, we would get what? Y prime plus, y prime times 2 square root of x plus y over y squared. It's going to give us negative 2 square root of x plus y over x squared minus 1. Well, 2 of our terms became a lot nicer looking. The other 2 became a little scarier, but you know, sometimes that's what happens in life. So what else can we do to this expression if we want to get y prime by itself? Laura?
You can factor out a y prime, and so then it would be y prime times plus 2 root x plus y over y squared.
Okay. That'll give us this equation. Y prime times 1 plus 2 square root of x plus y all over y squared minus 2 equals negative 2 square root of x plus y all over x squared minus 1. And then finally, I think there's one more thing we can do to get y prime by itself, to get just y prime as an expression in terms of x and y. It's going to be our last step here. Rachel?
Divide both sides by 1 plus 2 square root x plus, yeah, that one.
This stuff. Yeah, we could divide both sides by this expression to get a y prime by itself. In which case we'll end up with, oh boy, negative 2 square root of x plus y over x squared minus 1, all divided by 1 plus 2 square root of x plus y over y squared. Fractions within fractions. Alright.
Could we, instead of multiplying both sides by 2 root x plus 1, could we have factored out y prime right there?
I think so. I think we could have. I think multiplying both sides by 2 square root of x plus y made the equation a little nicer looking, but I don't think it was a strictly necessary step in order to get y prime by itself. So if we had done that, we would have gotten y prime times what? 1 over 2 square root of x plus y plus 1 over y squared equals blah, and then we could have divided both sides by that stuff. The stuff we factored y prime out by to get y prime by itself there. And I think that would have saved us like maybe one step. And we would have gotten an answer that looked a little bit different, but came out to the same thing. Yeah, good question. And if we really wanted to, we could do something like multiply top and bottom by x squared, and then multiply top and bottom by y squared. And that would have the effect of getting rid of the fractions within fractions. What would that give us in the end? It'd be something like negative 2 y squared square root of x plus y minus y squared over minus x squared y squared over x squared y squared plus 2x squared square root of x plus y. Which, I don't know, if you think that looks a little bit nicer, then you can go with that. It doesn't have fractions within fractions anymore, which can be good. But I would accept that or that as an answer. Some expression that has y prime by itself. So, moral of the story is, if you want to find y prime in an expression like this where y's are on both sides of the original equation, you're probably going to end up with something like this, where you have y prime terms showing up on both sides after you do the initial differentiation step. And if you have something like this showing up, it then comes down to a matter of manipulating both sides that all your y prime terms are on the same side, which led us to here. Here we subtracted this term from both sides, added this term to both sides so that both y prime terms were on the left-hand side. And then we could factor out a y prime from the left-hand side, once the left-hand side consists of all the y prime terms, and then divide both sides by all of this gobbledygook to get y prime by itself. Any questions, comments, or concerns? All right, in that case, it is time to go for the jugular. I'm going to go ahead and skip the next page, leave it to you all as kind of an exercise. If you want a little bit of extra practice with this. We're going to look at the last page, where we're going to be doing something slightly different. We're going to be looking at the curve 3x squared plus 4y squared plus 3xy equals 26, which is going to look something sort of like a circle, except it's a circle that's been punched in the gut. Now it looks a little bit sideways, a little bit tilted at the world. And our goal is not just going to be to find y prime this time. We're going to be doing something a little bit different. We are going to find all points on the graph where the tangent line is horizontal. So, what do I mean by that? Well, when the tangent line is horizontal, that means we have something that looks like this, where our slope, where if we take a tangent line, it becomes just this horizontal line with a slope of 0. So, just looking at our graph, how many points can you sort of see on the graph, just looking at it, where it looks like we might have a horizontal tangent line? Anna?
2.
Approximately where? Yeah, sort of like the top and the bottom. If it was a perfect circle, we'd say the exact top and the exact bottom, and they'd have the same x-coordinate. But to me, I would say it looks like we maybe have a point here where we have a horizontal tangent line. And maybe a point down here where we have another horizontal tangent line. And the question then is going to become, how do we find out where these points are? These 2 points on our graph where it looks like our tangent line to the graph comes out to something perfectly horizontal.
Well, if you take the derivative of the function, it'll be equal to 0, so that you can find the slope at that point. That's where the graph is equal to 0.
Ah, okay. So we want to set the slope equal to 0, which I agree. If our tangent line is horizontal, that means that it has to have a slope of 0. So I think I like what your idea here of we can find y prime, or dy dx. I think you wanted dy dx last time, so we'll do dy dx. And then set that equal to 0. And see if we can solve for the points on this graph where we have a horizontal tangent line. So yeah. So This ultimately comes down to find y prime and set equal to 0. So let's do that. All right, we're going to find y prime. As always, I'll do the hard part. Derivative of 26 is going to be 0. Let's see. Logan, what are we going to get if we differentiate 3x squared with respect to x?
We're gonna get 6x.
Yep, that one. That term's going to behave like it normally does. Vera, how about 4y squared?
8y times y prime.
8y times a y prime. And please, Helen, we're going to make it a dy dx. And here's going to be the tricky one, I think, this time. How are we going to differentiate 3xy with respect to x? Sam?
Product rule.
Product rule. Well, we have an x, and we're multiplying by some functions, y, in terms of x. So I think, yeah, to differentiate this, we will need the product rule. Give myself a little more room here. Okay, so Sam, if we take first term, I'm going to just factor out a 3 from this whole thing, so we're really just differentiating x, y. What are we going to get if we take first times derivative of second?
X times dy dx.
11x times a dy dx. And what are we going to have to add to that?
Just plain y.
Plus the derivative of the first term, which is just going to be 1 times a y. And I think we'll end up with this. 3 times the expression x times dy dx plus y. And so if we multiply this all out, we'll get a 6x plus 8y times dy dx plus 3x times dy dx plus 3y is going to be equal to 0. Vito Dorito. Unfortunately, we can't just factor out a dy dx here from the left-hand side because we have some terms with dy dx's in them and some terms that don't have these terms. So what can we do first in order to get only terms with dy dx on one side? Laura?
You can move the 6x and then 3y to the other side.
Okay, so if we subtract 6x and 3y from both sides, I think that's going to give us an 8y dy dx plus 3x dy dx is going to be equal to negative 6x minus 3y. What can we do now? What can we do now with this equation? Rachel?
Then you can factor out the dy dx on the other side.
Okay. I'm going to move over here so we have a little more space to work with. So what'll we have, Rachel, if we factor out a dy dx?
It'll be dy dx times 8y plus 3x.
Okay. And that'll be equal to the negative 6x minus 3y term. And finally, Tara, what do we get now when we do something to get dy dx by itself?
So you divide both sides by 8y plus 3x, and you'll get negative 6x minus 3y over 8y plus 3.
Like that? I like it. Yeah, dy dx is going to turn out to be negative 6x minus 3y all over 8y plus 3x. Unfortunately, this is not the end of the problem. The hill does not continue. Because we need to not only find y prime in this problem, but to find our points where we have a horizontal tangent line, we needed to set y prime to be equal to 0. And then see what happens. So we need to find the points on our graph where negative 6x minus 3y divided by 8y plus 3x comes out to 0. Golly, how do we deal with such an equation? Whew. Right now we have lots of stuff going on. We have a fraction where we have negative 6x minus 3y divided by 8y plus 3x. Out of curiosity, what would we get if we multiplied both sides of this equation by what's in our denominator, 8y plus 3x? Celia, what would we get on the left-hand side if we multiplied our left-hand side by 8y plus 3x?
The denominator would cross out, so it would be negative 6x minus 3y,
And on the right side,
0.
0 times who cares is going to come out to 0. So in order for this equation to be true, we need that the numerator of this fraction comes out to 0. If the denominator is 0, then dy dx is undefined. So we need the numerator to come out to 0 here. And let's see. I'm going to add 6x to both sides and divide by negative 3. And if we divide both sides by negative 3, what will we end up with here? Okay.
Negative 2x.
We'll end up with a negative 2x. So in order for our fractional dy dx to come out to 0, we need that the numerator has to come out to 0. And in order for the numerator to come out to 0 like this, it has to be the case that y is equal to negative 2x. Yeah?
Wouldn't there be 2 points though?
Oh my gosh. Anna, you said you wanted there to be 2 points. How many points are there where y and negative 2x are equal to each other? Just in general, how many coordinate pairs are there of x comma y in the plane where the y coordinate is equal to negative 2 times the x coordinate?
1.
1? What is it?
Oh, sorry, no. This should be an infinite, right?
Infinite.
Because it's just a line.
Y equals negative 2x. Oh my gosh. That gives us an entire line of points. Specifically, infinitely many points. But I don't want infinitely many points. I want 2 points. I want these points. I'm going to draw these on the same graph just for fun. Let's do that do that in yellow. So here I'm going to try and graph out y equals negative 2x. And it's going to be a line that looks something like that. We know that dy dx needs to be 0, and that if you're looking at points on this curve specifically, dy dx is going to be 0 if y is equal to negative 2x for points on this curve. Laura, you have an idea?
Could you take negative 2x and plug it in for y in the original equation?
In the original equation, so in other words, you want to find where sort of this line intersects the original white blob shape? I think that would give us 2 different points of intersection. I think that would work. Because if we find the points on this original curve, 3x squared plus 4y squared plus 3xy equals 26, if we can find the points on that curve where y is equal to negative 2x, I think that'll give us the 2 points we're looking for. So there are infinitely many points that satisfy y equals negative 2x, every point on this line right here, but I think only 2 of those points are also going to be on our original white curve that are going to satisfy the equation 3x squared plus 4y squared plus 3xy equals 26. And so, Laura, I like your idea of trying to find where the 2 curves intersect then to tell us where those points are going to be. Hopefully there's 2 of them. If we come out with more or less than 2, then something's not horribly wrong. Okay, Laura, you suggested something earlier for how we could go about finding where these 2 curves intersect. Can you repeat your suggestion?
To plug in negative 2x everywhere there's a y.
Okay, so substitute negative 2x for y, so that our original curve is just written in terms of a single variable. Sounds reasonable to me. Let's try that. So now we can substitute y equals negative 2x, and then I think we'll end up with an equation where we can solve for x. So let's see, if we do that, we'll get 3x squared plus 4y squared. Well, y is negative 2x, so that'll give us 4 times negative 2x quantity squared, plus 3x times y, so plus 3x times negative 2x, is going to be equal to 26. So this will be the equation we get when we make the substitution that Laura suggested. We swap out all of our y's with negative 2 x's. What are we going to get if we take 4 times negative 2x quantity squared? Avery?
So whenever you square the negative 2x, then you're going to get 4x squared, and then you multiply that by 4, so you'll get 16x squared.
Sounds good to me. Negative 2x squared, if we take negative 2x times negative 2x, we'll get a positive 4x squared. And when we multiply by this 4 out in front, that'll come out to 16x squared. How about when we take 3x times negative 2x?
Negative 6x squared.
It says we get a negative 6x squared, which I am on board with. Oh, hey, got a lot of x squared terms popping up here. That's kind of cool. 3 plus 16 is 19, minus 6 is 13, so we'll get 13x squared is equal to 26. If 13x squared is 26, what will x squared be? What was that? Divide both sides by 13 and 26 over 13. That's nice. Just comes out to 2. And if x squared is equal to 2, what does that tell us about what x should be equal?
Plus or minus the square root of 2.
Ooh, it didn't fall for the trap. Yes, it's going to be plus or minus square root of 2. The trap being forgetting about the minus. So it looks like x can be one of two things in order to give us points that we're looking for. One last thing though. Our original problem was not just to find the x coordinates where we have a horizontal tangent line, it's to find the full points, x comma y, where we have horizontal tangent lines. So if, let's say x is square root of 2, how can we find what y is equal to on this surface? So I think we're going to be looking at this bottom right point here. Josh?
Couldn't you plug it into our y equals negative 2x, but use the negative value for that one?
Ooh, sounds good to me. Yeah, we could plug it back into the original equation and solve for y. But we also have this much nicer looking formula down here. So Josh, I'm glad you suggested this one. Yeah, we could use the fact that y equals negative 2x. And say y is going to be negative 2 times that to get negative 2 square root of 2. And finally, how about if x is negative square root of 2? What's the y coordinate going to be of this point on our curve? Huh?
Positive 2 root 2.
Y is going to be negative 2 times negative square root of 2, which will come out to positive 2 root 2. And so now we're finally ready to write our final answer. Looks like, Anna, I think your intuition was right. We are going to end up with two separate points where we have this horizontal tangent line. The first is going to be at square root of 2, comma, negative 2 root 2. And our second is going to be negative square root of 2, comma, positive 2 root 2. Give you the location of our 2 points where we have a horizontal tangent line. So we found y prime using implicit differentiation and set it equal to 0. We got this equation y equals negative 2x when we did that. We then substituted that back into our original curve to find the 2 points that were on our curve and that satisfied y equals negative 2x. How about that? We just finished standard 8. Okay, before we leave, I have a question for you all. Would you like me to put a standard 8 question on the exam?
Yes.
Yes.
Keeping in mind that if you don't want to do it, you can just skip it and come back to it later.
100%. Just put like,
Well, that is a very positive remark.
put all 22 on there.
No.
That'd be pretty great. No, because
I'll be there
I
in 3 hours.
I know some of the stuff that's.
Take care. Yeah, have a good day, everybody. I'll see y'all on Friday for our standard 1 through 8 exam.
Tomorrow, coming in the 1 to 2 time, could I retest or pass on one of the standard numbers?
Yeah, I'll let you do multiple if you prefer. Or you
call.
can try it out do one at a time.
I'll probably just do 4 and 5.
Okay, send me an email to remind me and that should be fine.
Thank you.
Hold on just a second.
Oh, yay.